All right, so this is day 3 of multi-level modeling. Today, my goal is to review linear regression, multiple linear regression. And I have a PowerPoint slideshow we're gonna go through to start that process. I also would like to look at a couple things on homework 0. The purpose of homework 0 was to get all of our computers, our studio, LaTeX, all of that functioning and talking to each other so that we don't have to worry about that ever again this semester. We want that to just go smoothly. We want all those kinks worked out now, right up front in week 1. So we'll do we'll get everyone's questions on homework cleared up in the first 10 minutes, hopefully. Then we'll go over the PowerPoint on linear regression. Then next class time on Thursday, we're gonna do examples. That will be a really lab type day, and I'll send out the file, an announcement of the files you'll need to download to have ready to go if you wanna follow along on your computer for Thursday. So Thursday we'll be actually doing regression in R, and that will be the homework that we're going to do for this kind of chapter unit on refreshing multiple linear regression. So hopefully you guys have read it. Lots of people have posted on the discussion boards. Even if I haven't commented a lot on my phone, I could read the discussion main post, but it was hard for me to view the comments in line on the app. And I was out of town this weekend for the Labor Day weekend. So I just got home about an hour ago because of the storm last night. So even if I haven't commented, I've been watching your conversation on there so I can cater our discussion today in class about the things that you guys brought up on multiple linear regression. And I really want to emphasize that. Today is a conversation about multiple linear regression, and then Thursday is a lab for doing multiple linear regression. I am not here to lecture you today because you've already learned this material in the past, and hopefully you've read your refresher material. So today is more of the conversation to what is it that we still need to talk about to get us all up to speed so that we can move forward, because multiple linear regression is one level, and what we're going to start doing next week is multi-level regression. And so all of the pieces of regressions, assumptions, beta weights, R-squared, interactions, categorical and continuous covariates, all of those things play equal roles. The same things apply for multi-level regression. So we want to make sure we have the base foundation on single level first. So with that, first agenda item, things with R studio, LaTeX, knitting, basics, questions you guys want to bring up. Let's take the first at least 5 or 10 minutes to deal with your questions, and then I want to show you guys some things. So just go ahead and unmute and take it away if you have a question, comment, concern.
Hi, Sarah.
Ariel, yeah.
I know a few other people came across the I think it was like site proc error for the document knitted, and I'm wondering if this is going to cause issues with producing the bibliography in the future, or if you're aware of what that error is saying.
So I'm so glad that you guys told me about the error, and so many people chimed in and said, yeah, I had the same thing, because that's not one that I've seen before. Are you on a Mac by any chance?
I have a Windows.
You have a Windows, okay. It's not always that. So do you have R installed on the computer that you have Zoom on right now?
Yeah. Mm-hmm.
Can you bring that up and share your screen? And let's look at that exactly, since there are multiple people in the class having the same thing come up.
Okay, yeah, I am just gonna try to pull up the homework assignment and the right folder as well.
Okay, great. So while you're doing that, Ariel, let me go over some basics. So one of the nice things that our markdown can do is it can do citations and create the bibliography for you. To do that, you have to have the citations saved in a bibtec, a .bib file. Zotero and all of those publication managers can export all of your citations in a file of that format. All of them, when you go up to the menu at the top and do file, you can export and choose to export it as a .bib file. Then you save that .bib file in the same folder as your R Markdown notebook. and then you read it in with the YAML header. But this is really nice. You can do citations that are inline, in parentheses, multiple citations in the same parentheses, and it will format them APA, MLM, whatever format version, as long as you have the style file that goes with that.
Thank you, Sarah. Yeah, I have.
You found it?
Ready to go, but I don't think I can share while yours is going.
Oh, I have to stop share. You're right. Only one person can share at a time. Okay, so hover on the pictures. At the bottom of the screen in the center, the green square with the up arrow that says share, and then choose screen and share again. Okay, here it comes.
Can you see it? Did it come over there?
It's coming now. It says you started sharing, but I can't see it yet. I do see that some people had it frozen. Are we unfrozen for everyone else now? Or are we still frozen?
That was a couple minutes ago.
So it's unfrozen now.
Yes, unfrozen.
Okay, I'm going to keep that chat window up. Okay. Ariel, it still says that you started screen sharing, but it hasn't actually come up.
Okay, it says on my end that I'm sharing, but
at the bottom lower left-hand corner, share again.
Okay, share
probably.
Again.
Yeah, probably stop sharing and share again. It didn't happen smoothly.
Let me try again.
So I am at my home today instead of in my office. I'm hoping my internet's going to be strong enough. I kicked all my kids offline. The storm is what I'm concerned about. I didn't have enough time to get up to campus. Still just, oh, there it comes. There it came.
Okay.
Just took it a second. Okay, so if we go to the very top of your R markdown file, so you'll notice that there are two things in the YAML header that we had not seen before. One is it says bibliography, and that's telling R which file the citations are located in. And if you come over to the bottom left-hand file panel on the screen, the tab that says files, at the bottom of that panel, so all the way down, see, can you click on that? Yes, that file, and it will open it. This is what a .bib file looks like. And again, you can use Zotero or any of those other citation managers to export this. And so it has every single citation. So the first one is for core R. And I got this by in the console typing citation and then open round parentheses and then quoting base. So to cite base R, this is the citation. Now, they always start with an @ symbol and then a word. So it's a manual, a book, or an article, the type of material it is, and then curly braces enclose all the information. The very first thing is kind of a handle that you assign a shortcut nickname for that citation. So this one I'm calling R-Core. And then after that, you can have all the components of the citation. So this one has an author, a title, an organization, address, year, and URL. The next one down is citing an article, and its kind of nickname handle is PKG_LME4, because this is to cite the package LME4, which is going to be the main package we'll use in this class. And so you can get this citation in the console manual by typing citation, then in curved parentheses, quoting LME4, the name of the package, and it will spit this out. But so you've got to have this. This is a text file that saves as a .bib. So you'll notice that those handles or nicknames for those citations are _core and PKG _LME4. If you scroll down, there's some more articles and books. So there's the Finch textbook that you read, the Hoffman textbook that you read, and then Hawkes, our textbook that we have for our class, although it has the wrong year there. I changed it over to the 3rd edition, but I didn't change the year. That's bad on me. So my frequently way of giving a nickname to a citation, and this is common, is to do the last name of the first author and then the year. So you can say the Hoffman 2004, and that's its nickname. Okay, so Ariel, can you close that tab, that we're the .bib tab, and we go back to our file. So that's in the YAML header after date, it says bibliography in that file name that we just looked at. And then it says CSL, that's the citation style language file. So that says how to do APA 7 format. And then there's the rest of the stuff we've seen before. So I want you to go up in the magnifying glass right above where your cursor is now. It says YAML, Y-A-M-L. Would you type into that up above the YAML header where you have the title in your R file?
It froze on me.
Yeah.
So I think I missed something. You wanted me to type something in the YAML?
In the find box. So it's up in the upper left-hand corner. Yeah, where your cursor is. Oh, that's my cursor. In the upper left-hand corner of your screen, there's a magnifying glass.
Okay.
Oh, click it again. Yeah, there in the box. Now type R, the letter R, underscore core. So here in the text, in square brackets, we put the @ symbol R core. That will cite that handle. Uh-oh, it got moved over. It will cite that bibliography reference right there in APA format. Now go back up to where your magnifying glass is and type in PKG underscore. And see here, again, square brackets and an @ symbol, and then that nickname handle, PKG underscore LME4, it'll correctly cite that in the parentheses. And anything that's cited in a sentence of the text will automatically have its citation show up in the bibliography. So why don't you go ahead and hit knit, and let's see if we can get that error to be produced again. So what's happening when you push knit is in the background, R opens a fresh copy of this file, and it starts at the top and it runs each chunk going down. And so you're getting information on each of these chunks moving down, and it converts it from R markdown to regular markdown, and from that to tech, and that happens with the knitter package, and then it uses LaTeX to convert it to a PDF, and if that's successful, it deletes all the intermediate files. So here you got it to knit just fine. Let's see if we get the error. So right now you're on the, this is the console window. Yeah, we don't, or the R markdown window, you don't, this time we didn't get any error like that.
I saw it, Sarah, but then.
Did you?
Yeah, it came up right before the document opened.
Yeah, I saw that too. I saw the same thing that everybody's getting.
Let's see, where is it?
The Pandoc, like site proc.
So Pandoc is helping in that conversion process. So
I can run it again if you'd like.
No, here, let me request remote control.
Okay.
And then I won't have to be like poorly directing your mouse. Okay. Okay, so this is in the, so I'm going to come over here to the R Markdown tab.
Oh, okay, I see it
There,
now.
so there, reference R core without an underscore. So I know what it is. If I come over here and type R core, here's R core, but it's not supposed to be R core. It's supposed to be R underscore core, because there was no citation that was R core. It was R underscore core. So that was my fault. Now, I also want to point out some things for everyone. So notice the tabs up here. The name of the files are in bright white, except for this file is now kind of grayed out and there's an asterisk at the end. This means we've made changes to our file and haven't saved it yet. If I push the save button, and that's a single floppy disk, it saves it. Now it goes to bright white again with no asterisk. And that indicates all changes for this file have been made. Another couple things I want to note. When you hit the knit key, it will always save your notebook, create your PDF, and your PDF is already saved. You don't, when you knit, if you knit and it knits without errors, you will automatically in that process have saved both your notebook and the PDF. The PDF is in the same folder. It's named the same thing as the R notebook, just with a .pdf, and it's already saved in that folder. You don't need to go here and worry about saving it. You can just close the PDF. It's already saved in the same folder. Okay. Those might be some things that have not been blatantly obvious if you haven't used R a lot in the past. Does anyone have, so if you had that error, what you need to do is go into your file, click on this magnifying glass so you get the find and replace, and find R core and change it to R_core. It was a mistype on me. If you replace all those, which there should only be once, and I've already done it, then when you knit, you shouldn't get that, because it was trying to make a citation on something that didn't have a entry on the BibTeX file to match it.
Thank you.
Okay, so if we go down in your PDF, and we can make it bigger because it's tiny, right? So I think it's right after this. Yep, so see, notice in this sentence, and it's indented because it had the sideways caret, the greater than symbol. Notice how I said in square brackets, I said @ and then the nickname handle R_core. Now it has been knitted to be an APA parenthetical citation. And then I had square brackets with an @ that said PKG_LME4, and now it's been replaced with the parenthetical APA citation of the article on which you should cite for LME4 package. Okay, yay, we've got that figured out.
Yeah, thank you so much.
Okay, other questions? I think a couple people made comments like, man, getting LaTeX to run was a bear. And the answer is yes, it is a bear. But the good news is you only have to do it once. And after that, it's well worth the hassle it has been. Okay, anyone think of anything else? Okay, I want to show you a couple things before we move out of R into doing reviewing multiple linear regression. So in R, I want to show you, I think I showed you this before, help cheat sheets. I want to go to the one on R markdown. There's an R markdown reference guide, which is longer, but I'm going to go to this R markdown cheat sheet. This has some good shortcuts for things, knowing what you can do in R. So it talks about R markdown. On the back side of this page, it has some Pandocs markdown. So this shows you, here we've got 2 columns. It has over here on the left-hand side what you would type, and then on the right-hand side it has what it looks like after you knit. So plain text, you just type plain text, it looks like plain text. Somebody asked, can you change the font and size of the font? Yes, but not easily. And so we're going to let it be. If you end a line with 2 spaces, it will start a new paragraph. And you can always add extra blank lines. So I use the enter key. I do 2 spaces at the end of the paragraph and enter, so I get a visual break. Italics, you make italics in your knitted document by putting 1 asterisk before and at the start and end of where you want the italics to be. 2 asterisks at the start and end of some text will make what's between it bold. If you use this back tick, it will make it look like code font. See the difference between this verbatim code? It looks like a different font than regular plain text. You can also do powers, superscripts, by doing a caret. And you can do, if you do a tilde before and after, it'll make a subscript. So if you wanted to write like a chi-squared, the chi symbol with a square, or something like that in the middle of a sentence, you can do that. Strike through is double tilde, and that tilde wave, that's on the back tick key above the tab key on the upper left-hand part of your keyboard. So there's some things you can do. Now you can do equations using LaTeX equation editor, and in a sentence you do $1 and standing alone you do double $signs. If you're interested, I can send you some really good websites for doing this. I'm not going to focus on that in our class. But we did do block quotes where it's indented on both sides. That's the sideways. And then we talked about, yay. All right. Let's see, where were we? We were in R, and I was showing you how to do things in LaTeX. So a couple things, I did show you how to do a figure. There were a couple of figures getting added into a LaTeX document, and one had a caption and one didn't, I believe. To do an unordered list, you can use the asterisks to do the main bullets, and then more indented, a plus to do sub bullets, and more indented and a minus to do a sub bullet on an item list. You can also do numbered lists and unnumbered lists where you don't know what the number is going to be, or the list is going to continue after some text. So, and somebody said, how do I do a table? Here's the slick way to do a table. And again, this is not content for this class. This is just inquiring minds wanted to know. And so if you want to have a horizontal break, like a line across your page, you could just do at least 3 asterisks in a row, and it will make a horizontal line break across your page. So, and footnotes I almost never do because they're not really APA, but here are some other ways to add some formatting into an R Markdown document as far as the text part of it, not the code chunks. And if you wanted to know what things can you put in the YAML header, here are some of these are the chunk options. YAML header, I think it has all of them. Most of them I think we've already done. Anyway, so those cheat sheets under the help menu can show you some more things you can do. And also if you Google or ask me, and I can tell you whether or not I know how to do it or I think you can do it as far as formatting in a document. So here's adding a figure with some text underneath it. Okay, so that none of that is actual statistics, but just kind of good to know. So let's go on to regression. So again, here is our Canvas class, and I am getting the slideshow I'm using. If you go into the Files section, under Psych 7650 Lectures, under the Lecture 01 Review Regression. So this is Files, and then the Psych 7650 Lectures, Lecture 01 Review Regression. There is one thing in there, and it's this PowerPoint slide that we're going to go over today. And you can download it, or you can just watch it on my screen because I'm going to share my screen. But if you want to refer to it, there are a lot of slides on here that we are not going to get to today. There's a lot of supplemental slides at the end, things I'm not going to focus on, but if you're interested, you might want to look at them. But let's go over the basics of regression. Okay, again, this is not supposed to be a lecture. I don't want to lecture you guys. You've already taken, a class on regression. This is more of a conversation for things you want to know about regression. And I'm going to have to kind of make it so I don't see everyone's pictures to see this. So these are some pictures we usually draw when we're talking about regression. This top one's 2D. We have a predictor we usually draw on the x-axis and an outcome usually on the y-axis. This represents if we have a continuous numerical predictor and a continuous numerical outcome. This picture below it is extending it to where we had 2 predictors and 1 outcome. So it's a 3D picture. In 2-dimension, regression fits a straight line. In 3 dimensions, it fits a plain flat surface. And I don't know what it looks like in more than 3 dimensions because my brain doesn't work that way. But the key here is we have a statistical method where we have 1 dependent variable with 1 or more independent variables. And we usually call the dependent variable y. Sometimes we'll call it the outcome. Those words I use interchangeables. The y variable, the dependent variable, the outcome. The independent variables are the x's, the x variables. They are the predictors. Sometimes I'll call them predictors instead of calling them independent variables. Mathematically, they mean the exact same thing. So someone had a comment about independent variables. Are they predictors, or who had that comment about with regression? Are we doing prediction or are we doing explanation? Did anyone remember saying something about that? So
I think that was me. I brought it up about the difference between, yeah, I think that was me.
Okay. So can you say a little bit more about that? Where have you seen that or that issue?
Can you repeat really quick? Because maybe somebody commented on it too.
Yeah, so I should have brought it up probably on screen. So sometimes we say that the independent variable predicts the y, or the dependent variable. We say this language of prediction, but sometimes we don't want to necessarily predict what someone's depression score would be. We want to understand how variables are involved in interacting or influencing a depression score. And so we could say that our x variables are predictors. We can say that even if our point is not to make predictions for new people, but to understand the interplay between variables. So how they come together to influence a score. So usually in research, your domains of research, you're more concerned with understanding the who, what, why, when, where, how variables come together and work together and influence each other. In business and marketing, they're more concerned with prediction. So like Amazon and Netflix, they're more interested in collecting data to make a good prediction for what you would like next. Because if Amazon shows you products you might also like, you're more likely to buy them. If Netflix can show you a movie that you might be interested in, they're more likely to keep you watching and therefore paying their premium. So they don't really want to know why you like the kind of video you like or the kind of product you want. They just want to make a really good suggestion in the future. Usually for research, our point is not to make really good predictions for new people, but to understand how these concepts come together, have more of the understanding. So even though we say predictor and making a prediction, that can give us information in regression about how variables have interplay between them. So we could say that net of socioeconomic status, the role of teacher influences the math score this much. And it's not that we want to predict new math scores, but we want to understand the influential relationship. And we're using regression, which can be used as a prediction tool to do that. Okay. Did that bring up any questions in anyone's mind you want to talk about?
I think I'm still just wrapping my head around it, because I think it feels like I don't understand it, but I think I just need to like sit on it for a minute.
And examples, probably need to see lots of examples.
Yeah.
Okay. Which we will be doing over this week with the homework and our lab more day on Thursday. So with multiple linear regression, the key is that your y, your dependent variable, must be conditional given certain values of x, or independent variables that are also called regressors. So we want to know, how does y vary with the predictors? Usually we're interested in how the mean of y reacts to different conditions among predictors. Now, you may or may not have seen this, but you can do regression for the median, for the 25th percentile, for the 75th percentile, for the 99th percentile. But we usually are more concerned with the mean because it has very nice mathematical properties. So usually when you've seen regression, it's regression for the mean. So here's a hypothetical example. So hopefully Candace and others, this will help kind of get our feet more solid on the ground. So say we have a dependent variable, we want to understand this general health. So we have a general health score. It's continuous, and we know that for different predictors, you might have a different distribution of this general health score. For instance, based on ethnicity, gender, and socioeconomic status, those three things may influence or have an effect, or different combinations of ethnicity, gender, and SES may lead to or be paired with a different mean value, different distribution of health scores. Now, this is an oversimplified situation to get us started. So here we're making each of these variables dichotomous, 2 levels. So we're saying ethnicity is black or white. Now, it's not that clear in real life, but again, simplifying, black or white. And gender, just male and female. And socioeconomic status, just rich and poor. We're going to just cut them into 2 groups to talk for a second. So here, there would be 8 different permutations or 8 different combinations of these 3 predictors, each of which has 2 levels. So there's 8 different subgroups within our whole population if we divide it these 3 ways. And we might be concerned, our research question might be, do these 8 different subgroups, do some of them have a different general health score on average than other of these subgroups? So if we go get a sample, in our sample, we would have some of each of these combinations represented, and we would want to compare their general health scores. Not for the purpose of predicting a new person's general health score, but to know how these 3 independent variables maybe work together to be associated with the general health score. So how could you do this? One way we could do this is we could make a plot, I love plots, of the general health scores of people in our samples based on which one of these 8 groups they're in. And so we could do 8 histograms or 8 box plots side by side, and we could look for a pattern. We could, for each of these 8 subgroups, we could calculate the 5-number summary or just mean and standard deviation and descriptively say, are these 8 groups the same or different? But what if I only had a sample size of 50? How many people are there going to be in each of these groups? Not very many, right? Maybe I would have 3 independent variables. There's some rule of thumbs that say for 3 independent variables, you should have 15 people per independent variable. That's 45. And if I round up to good number to be careful, that would be 50. So that only leaves about 6 people per combination, per cell, per combination of our predictors. That's not a lot if we're talking about doing mean, standard deviation, histogram. 6 is not a very big number. So we need some other way to be able to summarize this information. And really, really key point, and this is for all statistics, all models are wrong. This is a statistician telling you all models are wrong, but some models are useful. All models are a simplification of reality. And we simplify, like if I had all of the people in here, their heights, that's, a lot of numbers. If I had all the people at the university, their heights, that's a lot of numbers. And it was really clunky to have all of the numbers. So I might want to simplify to a mean. If I wanted to compare men and women, I could have all the men's heights and all the women's heights, but that's a lot of numbers to look at. I could collapse to average of men, average to women, and just compare the averages. That simplifies the comparison. Now, anytime we simplify, we gain something in the simplification. We've got less information. We have more condensed information to compare. We've gotten smaller as far as the numbers we need to compare. But we always, when we simplify, throw away information. And we want to be careful that what we're throwing away is not signal, is noise. We'd rather throw away noise, not signal. And so we want to use a model that picks up the important components of reality. And some models simplify more than others. And the simplification is the assumptions. So if I'm going to compare the average of men to the average of women, I am assuming that the spread in the 2 groups is irrelevant. That's homogeny of variance. When you do a t-test, we have the underlying assumptions that the 2 groups have the same amount of variation, the same standard deviation, the same variance, the same spread. And when we do an ANOVA, we do the same assumption. And how do we test the assumption of homogeny of variance for a t-test or an ANOVA? Anyone remember? You'll get a gold star.
Look at the QQ plot of residual.
For spread, we use Levine's test to compare the spread of two or more groups. So we have ways to kind of see if the assumption is valid, but the validity of assumption influences the rightness of the results of the test, or how much information we're throwing away. So if we had done this thing where we done the average and the standard deviation, or a box plot for each of those 8 combinations, we have a lot of things still yet to compare, and none of them would be very stable. So the more cells or combinations you have, the more groups you have to summarize, the more summaries you have to deal with later, and each cell or combination is going to be smaller. And so we might never have enough observations to fill or get accurate representation in every combination. So this is where regression comes up. This is kind of a way to deal with this summarizing each combination. Is regression is a way to compare the conditional distribution of a dependent variable in a simplified way. So what we do is called a smoothing technique. So I think this is going to be easier to see when we get to the plot. But it's important to note this last bullet on the slide. Smoothing always results in loss of data. But is the loss of data loss of information or loss of noise? And that's the choice as the analyst you have to make. So to look at this, here's fictitious data. This is really made up. I have a Y variable. Here's my Y variable. It's normally distributed. I'm going to have one predictor, and it's a 5-level categorical variable. Say these are 5 ethnicities, and I picked 40 people per group on purpose in my sample. And then Z is another variable. Maybe this is, we could be height and weight. We could be depression and socioeconomics, income. You know, we could label them whatever we wanted. We have a sample size 200. X and Z are correlated. So the different groups have different distributions, but this is the marginal or the overall distribution of this Z variable. X and Z are predictors or independent variables when it comes to our outcome or our dependent variable Y. Now here is a picture. On the x-axis, we have our one of our variables of interest, X, and it has levels 1, 2, 3, 4, 5. It has to be a whole number. It's a grouping variable. Our outcome Y is up the side of the graph, and this is continuous. If you look at that plot, hopefully at this point you guys can pick up something. What is the pattern you pick up when you look at that plot?
Positive trend.
Positive trend.
Are the 5 categories, or are they scale?
Well, they could be either. Let's say it's an ordinal. So even if they're categories, they have this order from 1 to 5. Whether this is a Likert scale, or this is grades 1 through 5, or first visit, second visit, third visit, fourth visit, whatever it is.
The middle level is more compressed. I mean, there's more spread on the outer levels.
Yeah, so we can compare the averages in the groups, but we can also compare the spreads. Is the spread important or not? Are the spreads exactly the same, or pretty close to the same, or vastly different? Do we want to throw away the information on the spreads? Is it relevant or not? Those are questions we need to ask about the thing that we're studying, which here is fictitious example. I want you to look at within, I color-coded this rainbow style because I'm a visual kinesthetic learner. We could think of these as strips. Now, when I've outlined them, you can see what Michael noted, that the green center group number, when X is equal to 3, is a little bit more compressed, definitely more compressed than when X equals 5. There's a lot more spread outness in that purple X equals 5 group. What regression is doing is it's looking at the averages. It's smoothing the averages. So inside of each of these strips, I've marked the average. I actually have the data, and I found the average. And so there are the average numbers, 4.67, 11.1, 13.5, 16.2. And when you draw the average, you want to find the line that fits the averages the best. That's what the regression line is doing. It's finding the line of best fit on average. Now, X here is a categorical variable, so we could picture a line going through those averages. If X is a continuous variable, it's almost like it does a moving window, and this would be like 5 spots it stopped at. So we want to look at the conditional, meaning at each point on X, what does the average of Y look like? And in a smoothed out way. Here are some ways of looking at it with a lattice plots, which we don't use a ton anymore. It's another way to look at a third variable. I want to skip some of this. Okay, right here, what I've done on this plot is I have connected those averages with a connect the dot line like we did in elementary school. When you just connect the averages, you get a broken line. It's got these breaks in it, or they're not really bends, they're not round bends, but they're flexing. If you were to smooth that out, that's what the regression line is. The regression line is a smoothed out average line. I think that's a better way to think of it. Now, sometimes we call it the line of best fit. It's the line of best fit. It best fits by minimizing the residuals, so minimizing the error. And that's probably how you learned regression, was minimizing the residuals. But sometimes it helps to think of it more as a smooth average line. So on this, we can say, on average, as you move from categories of X, each time you move to a higher category of X, the line or the average goes up the same increment. Every time you move over one level in X, you move up a certain amount in Y. Over, up, rise over run, algebra class. See, a couple of people have their mics unmuted. Is there something anyone wants to bring up here?
I was just going to ask, is that also called the least squares line? Like,
it's also called the least squared line.
Okay.
And so sometimes a multiple linear regression is called OLS, ordinary least squared, because one way you can find out where this line is to smooth it is to when you get all those residuals, you square them and add it up, and then you get the sum of squares. So when we do ANOVA, we have these SS, these sum of squared values, and we square it because some points are above the line and some points are below, and if we did the residuals and added them up, the positive ones and the negative ones would cancel each other out to 0. So that's why we square them. And so least squared line is the line that gives the smallest total of the squared residuals, the amount off the line each point is. Anyone else? This is the time to converse about regression.
I have a kind of a question.
Yeah, Michael?
So when we're reporting betas, typically we use the language is associated with a certain unit of increase of X, or is associated with the outcome variable. That's really a nice way of saying on average we can expect.
That's exactly what the beta is saying. So the beta estimates in regression say, on average, if X goes up 1 unit, whatever X is measured in, if X goes over 1, Y will go up if it's positive, or down if it's negative. This amount, the beta number, that far, it'll move that far. It's associated with the change that far on average. And we usually just say associated with if it's an observational study. You should never say causes or leads to an effect unless it has been X randomized, because you can only infer causal relationships in randomized study. In observational, we can only say associated with, and hopefully a mountain of evidence will eventually lead to a causal conclusion.
And I just clarify. Yeah. Thanks for the clarifying questions. And so an unstandardized beta is like within whatever kind of metric system or however they're gathering the data, like actually in those units. And
the units of Y. Yes.
in the units of Y, whereas like a standardized, everything is standardized around standard deviations pretty much.
Yes.
And
so
it's giving you that.
So that's an important distinction that we're going to look at more in depth on Thursdays. Unstandardized betas and standardized betas is not something we worry about too much in multi-level modeling, but it does come up as well. So I want to make sure we hit that on Thursday when we have a concrete example in front of us. Yeah, so here's another regression line. Now, let's see, take a chance and look at this. We still have X with 5 levels and Y being continuous, but there's a different pattern going on. Is this a negative relationship? Is there anything more?
Could be a quadratic, maybe.
Is it a straight line relationship? Yes. Carly says maybe it's
Quadratic.
Quadratic means like a parabola, a U-shaped, and here it would be an upside down U-shape. Does that line fit that data really well?
No.
And no, it's more like it goes up and then it goes down. Just because we're doing multiple linear regression, that does not mean that our lines cannot be curved. We can have curved lines in linear regression by adding quadratic terms. So it's our variable squared. And we'll see an example of this on Thursday. So I think I really want to point out that linear is not always the best. You need to plot your data, and that's why I spend so much time on plotting in this class, because you need to know if it's linear or quadratic before you fit a model. And you can also check which one's better by looking at fit statistics. Fit it with a linear, fit it with a quadratic, see which one fits your data better as far as a fit statistic. Like we're gonna do log likelihood, but there's AIC, BIC. For linear regression, there's R squared. To see if that pattern is appropriate. Because you can fit a line to anything, but it might not be appropriate for any particular data. So the rule is plot your data. Okay, so this is just a general introduction or overall big picture of what regression is. I have said nothing about slopes and intercepts, standardized beta, variance explained, how you select a model, confidence intervals. A lot of these things we haven't talked about yet, but we will. But does everyone, I hope it's clear that regression is just doing a smooth pattern on average about how each predictor relates or is associated with the outcome. Okay, applications. Why in the heck would we do regression? Sometimes we do regression to characterize a relationship, to say the strength in the relationship. If you have a regression model that has one predictor, the beta is the same thing as the Pearson's correlation between the predictor and the outcome. The dependent and independent variable, their correlation will be exactly the same as the beta for a simple linear regression. That's a simple linear regression means we have just the one predictor going with the one outcome. And we can put multiple predictors in to get partial correlations. We can use regression, multiple linear regression, to develop a quantitative formula, equation to describe how a dependent variable is predicted or influenced or associated with, I guess I should say more correctly, the independent predictor variables. We can add in these other covariates, other variables on the independent side of a model to control for effects of other variables. So this is something that's very important in observational studies. Everyone give me a thumb up or thumb down if yes, this is no, if yes, your field uses observational studies. 2 thumbs up, 1 thumb up. Julie, no observational studies in yours? You have more randomized? More observational. Most people that are studying human beings do observational studies. Why? Why don't we randomize more?
It's not always feasible.
Like, what would be something we can't randomize?
What school somebody belongs to.
What school someone goes to. Can't randomize that.
Or who signs up for your study.
We always have some selection bias for who's in our study. What about gender? What about race, ethnicity? Can we randomize those things? What about family history? Prior experience, attitude. Human beings come with so much going on that we have no ability, or it's just not feasible to change. Or like sending someone to a different school. Sometimes we can control that, but sometimes it's too big of a pain to do. Sometimes it's out and out just plain impossible. Sometimes it's just not worth it, or not. We just don't want to do that. We can also use regression to say, out of a set of independent variables, which ones have more predictive power or more influence over the dependent variable. So which one has more importance is often related to which ones have more predictive power. And we often use a partial R-squared to assess that. That's one way of doing it. The other way, and that's what a standardized beta gives you, is a partial R-squared, a partial predictive power. We can also compare different regression models, competing versions, to see which one fit the data better. So I've worked with someone before, might be you, who fit data, and their field had 3 different competing models or theoretical models for what influenced the particular outcome. I can't even off the top of my head remember if it was reading or I can't. Anyway, they had competing models. So they gathered some data that measured the things that were in these models, and they fit the models to see which one fit the data better. It turned out that none of them fit very well, so now they're developing their own theoretical model about how these things play together to influence their outcome. So their first stage of their research was which model fits better, which existing model fits better based on the literature. Another very common thing we use linear regression for is to assess mediating and moderating effects of one or more independent variables. And I want to spend a moment on these 2 words because they are used over and over again, and I had never heard them till I came to this college, the College of Education. These words do not exist very much in the land of pure statistics. They have some very specific connotations. Mediating is a directional path model. Moderating is when variables have a bidirectional interactive effect. And a lot of you, your dissertations are going to involve investigating one, the other, or both, mediating or moderating relationships. So we want to go over them a little bit more. Okay, so our equations, if we have 1 independent variable, think straight line, 2 is a 3D flat plane, or if we put in a quadratic term, it could be a curved surface. And 3 or more dimensions is called a hypersurface, which I don't know what that looks like because I can't see it. So simple linear regression is just what it says, simple, but often too simplistic. So multiple linear regression, the multiple in multiple linear regression means you have multiple predictors. That's different than multi-level analysis. And we'll see this next week, right? Fox. But multiple in the multiple linear regression, MLR, just means more than one predictor. And we can use ordinary least squared methodology. There is also another methodology called maximum likelihood. And for single level regression, they give you exactly the same results. So they usually teach in most classes multiple linear regression with the least squared approach because it's very visual. But the computer, I will tell you, most computer programs are not actually drawing a line, measuring residuals, squaring all the numbers and adding them up, and then doing it over and over again, the way that you were kind of taught to think about it. The computer is more likely doing what's called maximum likelihood, and that's what we're going to use in multi-level analysis. So we'll get into that more as we go forward. But same thing, we're trying to visually, it's finding that line of best fit. So question comes up. Simple linear regression has one predictor for the one outcome. If I have 3 variables of interest and an outcome, why don't I fit 3 simple linear regressions? Why do I have to fit a multiple linear regression with all 3 predictors at once?
You can have more error when you have multiple models rather than if you put everything into one model, there's less error.
So when we did the 6600 class, ANOVA, you can do lots of t-tests. If you have 4 groups, you could do lots of different t-tests comparing all possible pairs. But usually we do an ANOVA as the omnibus overall test first, and if significant, then we can do follow-up post-hoc pairwise test. And we need to use a method like Bonferroni, Tukey's HSD, Fisher's LSD to correct for making multiple comparisons. The same thing in regression. If by doing one model with multiple predictors at the same time, we can reduce the chance of inflating our type 1 error by making multiple comparisons. The second reason is by having all 3 predictors in the same model, we can not only look at each of their independent roles, but we can look for interactions between the predictor variables. So more complex relationships between our independent variables. And that's the moderating part, the moderating relationships. So let's think about, a lot of you may have a control group and a treatment group, whether you've randomized them or not, but 2 groups. So control, in a randomized experiment, the control group, you have randomly selected some participants to not get this treatment or intervention. Sometimes we use a waitlist strategy, so temporarily at least they don't get the intervention. And this is to control for the placebo effect. But that, when we do that, that's called experimental control. We can also do statistical control, and this is when we add other covariates to a regression model. So if we're doing an observational study, we can't randomize everything. But if we can't randomize something that we think is influential, could be a potential confounding factor, by including that component in the model, we can statistically control for it. So the regression coefficients don't just tell us the Pearson correlation, they tell us the partial correlation after controlling or net of the effect of gender and socioeconomic status. The teacher's affect has this effect on learning. So we can partial out or separate out the effect of one predictor from the others by having multiple linear regression, multiple variables in the model. And that's usually more important for understanding the relationship between variables. Okay, so here I have written the typical regression equation. Y is our dependent variable, and then we have betas, which I'm using a little b here. The new APA, somewhere here, the new APA 7th edition tells us when you're writing up your papers, be it student papers or manuscripts, the betas that you calculate, your estimated betas, you should use a little b, not a capital B, not the beta symbol, but a little b. It says so right here, and I can even give you the page numbers, but not right now. So we're going to use little b. So we have an intercept and then a little b estimate, a parameter estimate for each of our predictors. Predictor 1, 2, 3, on down. And at the end, we have an E or an epsilon, that's the error. And we are assuming that the error residuals for any individual are independent of each other. That's where we get the assumption of an independent sample. So this regression equation, now here I put a little tick by the Y. See that little quote tick? Sometimes in stats books, they usually put a hat on it, like that little kind of carrot stretched out. That's the predicted Y. So on average. So we have what the regression line predicts, and we have what we actually observed, and we have the residuals, how different those two are. And we can use those residuals to do diagnostics on the assumptions. So here's an example. I have 3 predictors, and case number 1 has the first predictor's 5, the second predictor's value is 4, the third predictor's is 10. If these were my betas, how would I get a prediction for that person? Here we got our equation. So the beta naught, that's the intercept. So we just take that value, 1.2. Then we take the betas 1, 2, 3, and we times each of those betas to each of the x values. So the first beta, 3.6, is what we multiply 5 by. 5.2 is what we multiply the 4 by. 4.3 is what we multiply the 10 by. And then we add them all up. So I can take my prediction line, and instead of putting betas, I'm going to put the actual numbers. And instead of putting the x's, I put the actual x values. That will get me, if I do my math and crunch my numbers, add it all up, I get 83. That's my prediction for that person. Now that person probably didn't have a score of exactly 83 on the outcome. Say they had 90. What's the residual or the error for that person? The regression predicted 83. When we measured them, they were actually 90. That's a residual or error of 7. So the squared residual for that person would then be 49. Usually we don't do that math to get predictions, like I say, for research purposes. So a lot of people talked about the assumptions in the reading being like, oh, I forgot the assumptions, or there's more assumptions that I remember. Right? Alejandro, I see you shaking your head, right? The assumptions. Assumptions are important. The number one assumption of multiple linear regression is that all your observations are independent of each other. This is where, if we don't have that, we should be doing multi-level regression. So this would be that all the students' math scores are independent. But if they're coming from 5 different classes, are they truly independent, or are they pre-existing in clusters? Is our sample of random voters, or are they voters that were selected based on being in households, so we have husbands and wives or cohabitating couples among them? If they're not independent, we should use a multi-level model. But you haven't learned this yet. So all you know how to do is treat them as independent. Now, somebody brought up on the discussion board, what if we have repeated measurements on person? So what if we had a pre-test, a post-test, and an 18-month follow-up? Can we treat those as independent observations? We could, but that, if I have 10 people and each person has 3 observations, is my sample size really 30? I have 30 scores, but they exist in clusters size 3 with a first, second, and third number. So not only are they in clusters of 3, but there's a distinction between which observation was first, which one was second, and which one was third. So they are not in a classroom. We just have students that are in a cluster. We don't really have first student, second student, third student generally. We just say that they are interchangeable in a group. But with repeated measurements, we have ordering. So it's more than just being clustered. We have a specific order within each cluster, and that order is over time usually. So longitudinal data. Usually, what would we usually do to study pre-test, post-test, 18-month follow-up? Who's done it before? What have you done with pre-test, post-test, 18-month follow-up? They're so common. Yeah, Allison?
Repeated measures ANOVA?
Repeated measures ANOVA, yeah. what's the difference between repeated measures ANOVA and just regular ANOVA? What makes it repeated measures?
You have multiple time points, right? And you're looking at the effect of time, change over time.
You're looking at change over time, assuming that each person may or may not have a different underlying person-to-person difference about them. In regular single level multiple linear regression, there's no way to do that. And so someone said on the discussion board, brought up, how would we do that? Can we do linear regression with repeated measures? And the answer is no, you cannot do repeated measures with linear regression. Unless you did something like, if you have just pre-test and post-test, some people will make the post-test the dependent variable and the pre-test a predictor, or a really common thing is they subtract the pre-test and post-test and make a change score or a gain score, and that's the dependent variable. And sometimes they'll put the pre-store as a predictor to control for it, and sometimes they won't. Those are options to force cluster data to fit into the square of regression, single level regression. And I am here, you guys are so great taking this class. If you have just a hammer, you're trying to hit everything with your hammer. Everything looks like a nail. But what if it's a screw? Maybe you need a screwdriver. So we're going to learn how to handle repeated measures, longitudinal data, with regression by doing multi-level regression instead of single-level regression. So sometimes multi-level models are called multi-level regression or repeated measures regression because we can handle that lack of independence. That's the first assumption for regular multiple linear regression. Multi-level models take regression and they relax this first assumption of having complete independence. Okay, that was what a lot of people said on the discussion board. Okay, these are the regular regression assumptions. How are multi-level regression assumptions different? And the difference right off the bat is the very first assumption is different. Instead of assuming that all of our observations are independent, we assume that there are clusters of observations, but that the clusters are independent. So observation 1, 2, 3 on me are associated with each other, but observation 1, 2, 3 on you are associated with each other, but you and me are independent of each other. So we allow there to be some correlation and then clustering, but net of that, we have independence. Assumption number 2 is that we have a linear relationship between our predictors and our outcome, our independent and dependent variable. We still hold this true in multi-level regression, but it's cluster specific. So there is a linear relationship between the independent and the dependent variable within each cluster. It can vary cluster to cluster, but it's appropriate for each cluster. Whether that cluster is a group of people or a group of observations on a person. 3, variance of the dependent variable is the same for any fixed combination of independence variables. So this is the homogeny of variance assumption. And we still have it to some degree, but again, it's cluster dependent in multi-level modeling. So the variance is the same across time periods for a given person, or the variance of test scores is consistent within each cluster, or it's similar between clusters. 4th, we have, now this is the one where I don't like the wording of this assumption. So I get misunderstanding, and I know we're just about up on time. I know we have 4 minutes left, so we are going to end on time. And again, what are we doing next Thursday? Examples, 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 the homework. Okay, we don't need that. Okay, so normal distribution. You've been drilled that the dependent variable y has to be normally distributed, right? That is not true. And this is where the people put that on a slide, and I have it on my slide, but let me tell you what it should say. The dependent variable is normally distributed for, oh, it does say, for all values and combinations of the independent variable. So it's the conditional distribution is normal. The conditional distribution. And I'm going to end it here. I will make another extra additional if anyone has like spare time, which I'm not banking on it. Where's my video of my little pen. My pen. Hold on here. Okay. Whiteboard share. Okay. I should make this on a slide because I do this every time. Okay. I had one of my first clients here came to me with data and they said, Sarah, help me. I have a Y variable that I want to do regression on, but the distribution of my Y variable looks like that. They said, what do I do? Can I do regression when my Y variable is distributed like that? And I said, well, what does your X variable look like? She said, well, my X variable, this was like this was a score on a science module, like the test score at the end of the science module. And it looked like that. And she goes, well, the X variable is like it was some predictor of that. And it looked like this. And I said, this is the univariate distribution of the predictor of the outcome, the dependent variable Y. And this was the unidimensional distribution of X. I said, what about the bivariate distribution? How would I look at the bi-distribution? I put X versus Y. Instead of having the count, a histogram. So these are histograms. I said, how do you make a bidirectional plot with two variables? What's that called?
Scatter plot. Normal Q.
Scatter plot. And she said, okay, let's make a scatter plot. And she started plotting the data. And guess what it pulled up to be? What does that look like?
A line.
It looked like a line. So even though Y was skewed, X was skewed. So when we plotted them together, what does that mean? Most people were really high on Y and really high on X. So what does that look like? Lots of people were high on both. And so when we plotted it, it looked like a straight line. So what's one of the things we do after we fit regression to check our assumptions? We do a residual plot. We plot the residual based on the actual value of Y, and we hope, if this is 0, that we see equal scatter above and below the line. We want normality of the residuals, not normality of Y. We want, and the way we look at this on the plot, if we look at it in a bidirectional, think of that plot we looked at before. For each slice of X, we want there to be a normal distribution around the average. So this has got a continuous X, but it's the same thing as that picture we looked at before with only 5 values of X. For each strip, for each particular X value, inside of there we have a normal distribution. And the spread in each strip, as we move all the way across, is about the same. And so I just want to really focus on that the regression can be appropriate even if Y is not normally distributed, because it's not if Y overall has a normal distribution, it's if Y has a conditioned on X has a normal distribution, and conditioned on X it has about the same spread for all values of X. And the way we check that is with residual diagnostics, and we'll learn how to do that in R on Thursday, because we're going to be doing that same kind of checks when we move to multi-level regression. Okay, so our time is up. I will stay on for anyone who wants to stay on for questions. I will leave the recording going if I think it's interesting, if it's not just personal questions, and then I'll get this up on YouTube tonight. So we'll see you guys Thursday. I'll do an announcement with the follow-up stuff about what you should be doing to prepare for class on Thursday, but you've done most of the reading, but I will have maybe point out again some of those videos that you might want to watch if you haven't already. Okay?
Thank you.
Okay.
Thanks, Sarah. Bye.
Hey, bye. Hey, Allison.
Okay, I am, I guess, the only one still here bothering you.
That's okay.
This stuff just really interests me. So, and I appreciate your passion for it. It's so fun to have a teacher who just loves what they do. That's really, I just had a quick, just conceptual question.
Mhm.
So I enjoyed one of the descriptions of all those different things you sent out last week of this regression stuff, which I enjoyed was, can I share a screen and maybe
I will.
draw something like you did?
Yeah.
Except actually, I'm not going to be able to draw really well because I don't have a.
It's okay. It's harder with the mouse, but you can do it. I can live with bad graphics.
Okay, can you see my white screen kind of?
I can.
So the way I was kind of understanding it and just conceptually with the regression made a lot of sense is the idea of comparing kind of, and you maybe remember even this graphic he did, if this is the kind of the least square line that you make and your points, and this is your
Data points. Yeah.
fit line. And then over here, if you're just thinking of all your, your Y's or all your outcomes, and you kind of the mean of it, you're comparing, and if I understood this right, you're really comparing all these little squared residuals compared to this mean line, taking all your little squared residuals compared to this fit line, and if this is however much better this line describes this data, really that's what, that's kind of, it might be even your R squared value, the betterness. Is that so far right?
Yes. So R squared tells you the proportion, or you can think of it as the percent of the variation in Y that's explained by X. So does X, so Y is not the same. So first off, Y cannot be the same for everyone, or else you can't explain what doesn't vary. You can only explain things that are different. So if everyone got a 4.0, then there's no way to know what's important because everyone got the same score. So if you have variation in your outcome, you want to know which predictor explains that variation, why not everyone got the same score. If different people in the population have different depression scores, what is it that explains the difference in the depression scores, or the difference in the math scores, or the difference in whatever it is, whatever the dependent variable is? We want to explain the differences. So that's another way. We want to explain the percent of variation. R squared tells you how much percentage of variation in the dependent variable all the predictors together explain. And partial R squares do that for each variable in the model.
Okay, I guess that's kind of where my question lies is, I can see this if this was just one predictor. Like, it kind of makes sense to me. I guess I could see it if you had another predictor and you could do like another one of these for that predictor. So you could have R squared for this one, have an R squared, if that's kind of like what you were talking about with the R squared. But putting with the idea of like the plane and having multiple predictors and finding the variance across the explanation of that variance across the multiple predictors, is it the same as just taking the R squared of this one, the R squared of this one, and then somehow, I guess then what do you do after you take those individual R squares of the different predictors?
So usually we don't do it, number one. We make the computer do it, right? So let me stop your screen, and I'm gonna draw on mine. Where did I put my, okay, here's my pen. So I'm gonna erase this all. How do I get it? erase everything now? Can I erase? I thought I could do erase. Oh, clear. There we go. Clear. I'll draw.
A little erase and scrape over.
Okay, I know. That's take forever. So now I want to draw. Okay. So if this is my y variable, and then this is my x variable, let's do this as my first x variable. If I have two x variables, and I'm not a good 2D variable draw. 2D. So x is like a grid if we have two continuous variables. So someone whose x's values are both 0 might be here, and someone's x variables who are both 5 might be up here, and then 4 would be here and here. It's hard. You would have this like 3D plane, and then your data. So you might have a point here that's above the plane, and then here might be a dot below the plane. So you get residuals that are, your points are above or below the plane. Because I can't, it's almost impossible to draw that. Let me go back.
I could see what you were doing though. That worked for me.
Let's go back. The first slide on here had a 3D representation, and you kind of have to think right here.
Yeah.
So we've got our two predictors, x1 and x2, and the regression is no longer a line, it's like a piece of paper. And if you have quadratics, then it can bend, like x squared, like, but if you're not doing squared terms, you just have a flat piece of paper, and that's that blue-green surface there. And so your regression, you have a regression surface. So points are above and below. So you can have your regression line tipped, your plane tipped in the x1 direction, and you can have it tipped in the y1. It's probably going to be tipped in both regressions. So the betas are the slopes on each edge. The edge that's like parallel with x1 and the edge that's parallel with x2.
Interesting. Yeah. Yeah, so those are the betas. Okay.
Yeah. So betas are slopes, but we've got a slope, if you have a piece of paper
both ways,
you've got a slope on this side versus the table, and you've got a slope on this side versus the table. So one side might be sloped steeper than the other edge.
Okay. And your R square, so in that
so usually when we're in social science, when we have predictors that are never truly completely independent of each other, what we do is if we have multiple predictors, we'll usually fit this plane with both predictors and then only remove one of the predictors. And then we can say the model with both predictors fits at maybe an R squared of 80%, but with only one of the predictors at 60%. By taking out one variable, we lost 20%. Our R squared goes down, or if we put it in, our R squared goes up an extra 20%. So those are usually how we prefer to say the strength of a variable is we do the model with and without that variable and compare the fit of the model with and without that variable.
Okay.
With everything else still the same.
Yeah.
And that's how we're going to do it in multi-level modeling.
Is it the same in the more predictors you add into that, the more like weird axes you would have, you can't
look at it.
Well, yeah, I can't think of it, but you would never necessarily in that case make the R squared could never necessarily get smaller the more you add.
Not in single level regression. And so that's where AIC and BIC numbers come in, because have you seen those before?
I don't know.
Okay, so if you add a predictor, your R squared is going to go up always. So every time you add a predictor, your model fits better, even if it's just fitting noise. So there should be some penalty. This is the thinking. There should be penalty for adding a lot of variables so that you don't just make a really, really complex model, because we want to balance fitting it well and parsimony. And so AIC and BIC are penalized R squareds, and they penalize it different ways. The R squared it's a smaller number, it penalizes the R squared, penalizes it different ways. One's more extreme than the BIC's. I can't remember which one's more extreme. AIC is used the most often, but BIC. So those are other information criteria that we judge model fit by, not just a straight up R-squared, but there's an adjusted R-squared and an AIC and a BIC to kind of get, yes, if it's better, you know, our R-squared goes up 2%, but we added 10 more variables. Is that really worth it? And so you do the same with multi-level models. What we're going to use is the log likelihood, and we're going to do a chi-squared test based on how many parameters we have to add to the model. We'll go over all of that in the coming weeks. But the main idea is, if we add a variable, does our model get better? If we take it out, is it just as good? Relatively good. And that's how we judge if a variable has an effect net of everything else that's already in our model.
Cool. Okay, yeah, that's all. Just some of those little questions on that.
Yeah.
Thank you.
So I didn't show it today, and I'll send this out in the announcement, but in the encyclopedia, so I'm going to go to the volume links. We're in software, and if we go to this regression book, this is what it's kind of 7610 type stuff. So there's something on correlation, simple linear regression, multiple linear regression. So this is from an intro stats with our book, in a blood pressure and obesity data set.
Oh, cool.
So we have a sex variable, which is 0 for male, 1 for female, and an obesity, which is actually the ratio. Like, if they're heavy, they're like 1.2 if they're 20% overweight. And if they're underweight, it'd be like 0.9. And this is based on this New York Metropolitan Life tables. And then they have their systolic blood pressure in this data set. So we have 102 people in this data set. The blood pressure on average is 127. The obesity on average is 1.31. So they're on average, they're 31% more than that table says they should. And so we can do, this is just showing some tables. So here's looking at pairs plots and looking at men and women separately, although men are pink and women are blue in this one, whatever. So this is like different ways you could look at the data. So here's like this is called a correlogram. So seeing if these variables are correlated with each other. And let's see, we'll come down here. So here's regression. So we can fit different regression models. So this first one has just an intercept. So what's the average blood pressure? This one says, does sex predict blood pressure? This one says, does that obesity index predict blood pressure? Does obesity and sex predict blood pressure? Does sex and obesity have an interaction with each other to predict blood pressure? And I'm saving these all, see this saving operator? And then I can use this TechReg or HTML reg to build a table to compare them all. So we've got the beta, so that every model has an intercept. And so this first model has no predictors, and its R-squared is 0. If you only have an intercept, you shouldn't be explaining any variance. And then this second model has sex only. And our beta here is 1.64, but it has a huge standard error, so it's not significant. Our R-squared is 0, and it penalizes based that we have another variable in there, so it actually makes the adjusted R-squared negative, which is not a good thing. This third model, the middle model, has obesity, and its beta is 23. So if our obesity index goes up 1, so that means if they are twice the weight instead of 100%, so 1.0 to 2.0 would mean exactly the table weight versus double the table weight, then our systolic blood pressure goes up 23 millimeters per mercury. So these are just unstandardized betas, so they're in terms of the units that the variables were measured in, milligrams per mercury. This fourth model has both independent variables, sex and obesity. And look, sex by itself didn't predict anything. Obesity predicts 11% of the variance in blood pressure. Together, they combined predict 14%. So even though sex didn't predict by itself, non-significant R-squared 0, when we add it to the model that already has obesity in it, it becomes statistically significant. By adding sex to the model that already has obesity, our R squared, which was 11, now goes to 14. So we gain 3% R squared. By itself, it doesn't do anything, but added to something else it will. And this is because we have an interaction, or we have some connection here. Is obesity and sex, is there a relationship? Are women or men more or less likely to be obese? If there is a correlation there, then we have multicollinearity potentially with fitting our model. And that's why you would think that sex has by itself has no R squared of 0. Obesity by itself has 0.11. So together it should be 0.11, but no, put together it's more. And it's because of the correlation that together they explain more than separately.
Well, and it's weird because it looks like there's not a significant interaction between obese and
this one there's not.
So it's, you would think you would see it. I would have thought I would have saw it there.
I think that it's here. If you check this out, here's a plot of the data. So the blue points and the pink points. I think here I made the blue are the boys and the pink are the girls. I don't have the legend showing here. And then I have the regression line for each group. So the men, they only go up to a little over 1.5. There's no one in the men's group that go above 1.5. But we've got some very obese women in this group. So, and we've got some skinny men, whatever, you know. So here, if we're looking at the slope of the two lines, that explains the variation. It looks like the pink line is a little steeper than the blue line. So it looks like maybe, but it might be just that we have a wider range of weight.
Yeah, it makes you think if you cut off all the women that are way heavier and see how that would adjust that, kind of the slope of that woman's line.
And that's when you really need to know your data, and plotting it can be one of the best ways to get to know your data and the idiosyncrasies with your data. And that's why I spend time going over plots, how to make them and looking at them, because you can learn so much about how your models are performing or which models you should do. And should we really be cutting out some of those extreme weight women, or should we be modeling men and women totally separately? We can start, you know, asking some different questions once we see the data.
That's cool. Cool, and we're gonna learn how to do some of those graphs and things like that.
Yep, but this encyclopedia is up there right now if you want to look at it, but a lot of this will be built into the class. So it's ggplot. We set our aesthetics, our axes, x-axis, y-axis, and I wanted to color by sex. To make the scatter plot, we do geom point, and I made them a little bigger so they show up. And then regression is adding geom smooth.
So I can go right in, use some of the and mess around with that.
Yep.
Awesome.
And here is where I'm selecting out the colors. It'll choose default colors, but I wanted males, I wanted it to say men and use blue. And for females, I wanted it to say women and use maroon. And so the color is for the points and the lines. The fill is for these like shaded ribbons.
Which I like those, yeah.
And then you can add labels. On the x-axis, the y-axis, the title. This theme DW I hit on that walkthrough. I like to have a white background, and that does that. And then this changes the tick marks. And then this is how you get the legend. That should have put the legend right in there. It didn't do. Oh, I know why. I know why it has having an issue. I'll have to fix this. Should put the legend where it should say a pink dot with pink shading, and it should say women, and a blue dot with blue shading, and it should say men right here in the corner. It's not showing up. I did something wrong. Anyway, so here's how you check assumptions with residual diagnostics. You say plot the name of which other model you save the name as, and you can, which equals 1 does this residual versus fitted plot, which equals 4 does this Cook's distance for looking at influential points. So it tells you that the observation 102 is one you might want to check because it's probably could be an outlier. And then there's also the CAR package has this residual plot, and it makes several different kinds of residual plots together to look at.
Awesome. I'll dig around in here a little, and
Yeah,
that's
so
really good.
so yeah, so there's lots of different things to look at. This is mostly here just for reference for your own interest.
I'll dive into it. Hey, well, thanks for so much time. And you spent a lot of time just with me, so I appreciate it.
No problem. Okay, bye.
Thanks, Dr. Morris.